Welcome back. This is the third video of section 4.2, in which we are going to talk about convex sets and linear operators in the weak topology. So let us formulate three results that you will prove in the exercises. We mentioned the first result earlier. It states that, so we know that in a norm space, a weakly closed set is a strongly closed set, and we saw that the converse is not true. However, the convex is true if the set under consideration is convex. Okay? And we proved a particular case of this theorem when we proved that the closed unit ball is weakly closed. Okay? This is actually a consequence of the Hahn-Banach theorem. Okay, so it's enough to take a strongly closed set and prove that it's weakly closed. How do I prove that? Usually to prove that a set is closed, we have two main strategies. Either that we prove that the complement is weakly open, in this case, or we prove that it's equal to its weak closure. In this case, I advise you to try to prove that the complement of C is weakly open. Okay. So by proving that it's a neighborhood of all its points. Okay. And we can deduce from this a corollary. So we know that a strongly convergent sequence is weakly convergent, but the converse is not true. However, if you have a weakly convergent sequence to element X, then we can find a sequence in the convex hull of the image of the sequence that converges strongly to X. What is the convex hull of a set? It's by definition the smallest convex set containing, in this case, the points X1, X2. So for example, if you just take 2 points, the convex hull of 2 points is just the straight line segment joining them. If you take 3 points, the convex hull is just the triangle. Okay, and so on. So, and you probably know that there's a characterization of the set. An element in the set is in the set if it is a convex combination of elements in the set. Okay, this is proved in an exercise of chapter 2. Okay, and the third result is the following. If we consider a linear map between two Banach spaces, now we know that on E there are two main topologies, two interesting topologies, the norm topology or the strong topology and the weak topology. And on this targets, so on the source space there are two possibilities, on the target space there are two possibilities. So we have 4 cases, but only 3 of them are equivalent. So if we put on the target and on the source space the norm topology, then saying that, so continuity, this is what we call continuity strong, okay? And this means that the inverse image of a strongly open set is a strongly open set. Or if you like, because it's a metric topology, if Xn converges strongly to X, then Txn converges strongly to Tx. Okay, this is the usual continuity that you know, and it's called also boundedness. Now, the other possibility is to put the weak topology on both the source space and the target space. So in this case, if T is continuous in these topologies, we say that T is continuous weak. Third possibility, we put the norm topology on the source space and the weak topology on the target space. In this case, if T is continuous, then we say that it's continuous strong weak. Okay? Now, it turns out that all these 3 conditions are equivalent. Okay? And the proof is not difficult, actually. So try to think of it. And it's better to use the closed graph theorem because it simplifies the proof. Okay. Now, what about the 4th possibility, weak strong? This possibility, this condition, so continuity weak strong, is stronger than all these 3 conditions, and it's equivalent to the following condition. So weak strong continuity for a linear map is equivalent to strong continuity and to the fact that T has a finite dimensional range or image. Okay, because we know that the range of T is a subspace. Now, it's not always the case that this subspace is finite dimensional. If it's finite dimensional, we say that T is a finite rank operator. Okay, so continuity weak strong is equivalent to continuity or boundedness, the usual property that you know, and to the fact that T has finite dimensional rank image or range. Okay. Okay, so this is explored in the exercise. Now, I have to mention that for a nonlinear operator, there is usually no relation between continuity strong and continuity weak. Okay, now, so this is, if you are interested, you can look at exercise 4.20 in the book of Brazis. However, for any map taking values in R from E to R, weak continuity implies strong continuity. Okay, and this is really easy. How do I know that? Suppose that phi is weakly continuous. Now, what topology do I put on R? I put the usual topology, or the norm, because the norm of R is just the absolute value. So the strong topology and the weak topology on R coincide in this case, because R is finite dimensional. Okay. So weak continuity in this case means that the inverse image of an open subset of R is a weakly open set of E. But a weakly open set is a strongly open set, and therefore phi is continuous with respect to the norm topology or the strong topology. Okay. And second remark, we assumed in the last proposition that the spaces are Banach or complete, because this assumption simplifies a little bit the proof, but actually the proposition is true without the completeness assumption. Okay. But it's a little bit more difficult to prove that. Okay, and now I come to an important topic, the weak topology as a vector space topology. Okay, now we know that we have, in a vector space, we have two fundamental operations, addition and multiplication by a scalar. And we can ask whether these fundamental operations are continuous. If we put the norm topology on E, then of course they are continuous, as you know from second year. Okay, in reason by sequences in this case. So if xn converges to x and yn converges to y, then xn plus yn converges to xn plus yn strongly in this, plus y strongly. And if alpha n converges to alpha in R and xn converges strongly to x, then alpha n xn converges to alpha x. You know that. But what if we put the weak topology on E? And the answer is yes, they are still continuous. Okay. So in general, a vector space equipped with a topology that satisfies, that makes these two fundamental operations continuous is called a topological vector space. Okay. So what we said means that E equipped with the weak topology is a topological vector space. Okay. Now we are not going to deal with topological vector space in generality in this course, but it's good to know that what we are studying is a particular case of a more general context. And of course, E equipped with the norm is a topological vector space. Okay. Okay. How do I prove that? This is a good exercise to test our understanding of the weak topology. Okay. So I have to prove that L is continuous at every point. So I pick an arbitrary point x0, y0 in E times E, and here, of course, when we say nothing, E times E is equipped to the product topology. Okay. And by the way, if you are interested, you can prove that this product topology coincide with the weak topology on E times E, because E times E is also a norm space. So there is a weak topology on E times E. But in this case, you can prove that these two topologies coincide. But we don't need that in this proof. Okay. So how do I prove that L is continuous at x0, y0? I have to prove that for any neighborhood V of the image, so of x0 plus y0 in the weak topology, there is a neighborhood in the weak topology of x0, y0 whose image under L is contained in V, right? So as we know, we can take V to be of a special form. So it is the set of z, if you like, such that fi of z minus x0 plus y0 is less than epsilon in absolute value. Okay, so we have finitely many elements in the dual such that V is of this one. Okay, so now I take Q1 to be the set V of x0, f1, fk, the same fi's, but the radius is epsilon over 2. So you can think of this as a ball. You can call it a weak ball if you like, but it has several centers and one radius. You can think of this in this form. It's not a ball actually, but you may call it a weak ball. So according to our definition, but instead of one center, I have finitely many centers and the radius. So here I take the same centers, but with radius epsilon over 2. Okay. So what does this mean? What's this set? By definition, is the set of x in E such that fi of x minus x0 in absolute value is less than epsilon over 2. And now it's easy to check that the image under L of U1 times U2 is contained in V, and U1 times U2 is just a neighborhood of x0, y0. Okay, by definition of the product topology. So how do I prove that? I take an element here and prove that it's here. So you take a paper and the pen and check that. Continuity of this, so this means that L is continuous at x0, y0, and since x0, y0 was arbitrary, it means that L is continuous everywhere. Okay, the proof of this, the continuity of the second operator is a little bit more tricky. So, but the same strategy, we take a neighborhood, a weak neighborhood of the image of a certain point, so alpha 0, x0, and we have to find a neighborhood of alpha 0, x0, whose image under T is contained in V. Same strategy. Okay, so I take M to be the biggest of these real numbers, fi of x0 in absolute value. So there are finitely many such numbers. I go from 1 to k. And I take delta to be smaller or equal than 1 and smaller or equal than epsilon over 2m plus 1. Okay, now, why did I choose that? You will see why. But this is something typical in analysis. So first, of course, you could take epsilon over 2m, but this is just to avoid the case that m equals 0. Okay, so in order not to distinguish between the case m equals 0 and m is different from 0, I just add 1. Okay, but the fact is that I just want delta to be less than epsilon over 2m for a reason that will become clear now. And I want delta to be less than 1 as well for another reason. Okay, you'll see why now. And now I take Q to be this weak neighborhood of x0 with the same functionals, f1, okay, but the radius is epsilon over 2 times the absolute value of alpha 0 plus 1. Okay, now, and we are going to prove that the image of this neighborhood, this is a neighborhood of alpha 0, x0 in the weak topology, okay, or in the product topology. This is the usual topology on R, and this is the weak topology on E. So same strategy. Okay. Now, how do I prove that? We take an element here and prove that it's here. Now, an element here is the image of an element in this product. So an element in this set can be written as T of alpha x, where alpha is here and x is here. Now, my choice of delta is less than 1. If alpha minus alpha 0 less than delta, then the triangle inequality tells me that absolute value of alpha minus absolute value of alpha 0 is less than delta, less than 1. So absolute value of alpha is less than absolute value of alpha 0 plus 1. So the ratio actually is less than 1. Okay. Now I use a fundamental trick. I add and subtract fi of alpha x0. Okay. So I write fi of alpha x minus alpha 0 x0 because I want to prove that alpha x actually belong to this set V. Okay, how do I prove that? I have to prove that fi of alpha x minus alpha 0 x 0 in the absolute value is less than epsilon. Okay, this is. So I rearrange this term, and now I use the triangle inequality. So when I take absolute value here, this would be less than alpha times fi of x minus x 0, but x is in u. So fi of x minus x 0 is less than epsilon over this quantity. So I get absolute value of alpha over this, which is less than 1. So in absolute value, this term is less than epsilon over 2. And with my other choice of delta, this is also less than epsilon over 2. So the sum will be less than epsilon. Okay. And therefore, this means that t of alpha x is in V, or alpha x is in V, because t of alpha x is just alpha x. Okay. So therefore, t is continuous at alpha 0 x 0, but since alpha 0 x 0 was arbitrary, then this means that t is continuous everywhere. Okay. Now, you may think that it's easier to work with weakly convergent sequences. So what if we take, for example, a sequence xn converging weakly to x and the sequence yn converging weakly to y? Then it's enough to prove that the sum converges to the sum. This is possible, of course, this is true and easier than this, but this just proves sequential continuity and not continuity. And we know that in a general topological space, sequential continuity does not imply continuity. So this is why we had to go back to the definition. Okay. And as a consequence of this, corollary 4.3, any two open balls, if you equip E with the weak topology, if you have an open space and we equip it with the weak topology, then any two open balls are homeomorphic, any two closed balls are homeomorphic, and any two spheres are homeomorphic. We know that this is true if we equip E with the norm topology, as it's not difficult to prove that actually, and with the same homeomorphism actually. But it turns out that this homeomorphism that I'm going to write now is both continuous in the weak topology and in the strong topology. Okay, so take two balls, two open balls. So they have, so first ball has center A and radius R, of course R positive, and second ball has center B and radius S positive. I want to show that these two balls are homeomorphic. So I just consider the map T from E to E given by this formula, B plus S over R x minus A. So what does this mean geometrically? X minus A is a translation, right? S over R times this is just a homotopy of center 0. And this is another translation. So T is just a combination of translations and homotopes. And according to what we said, translations and homotopes are continuous in the weak topology, okay? Because they are just, this is a particular case of the more general, the previous proposition. So this proves that T, of course, T is continuous in the strong topology. Okay, so continuous strong. Now it's not linear, so I cannot directly deduce that it's continuous weak, because we have these translations. But according to the previous theorem, T is continuous weak, right? And T is invertible actually. If you just solve this equation, call this y, you can solve x in terms of y and you get t minus 1. Okay. So if you think of it geometrically, it's easier because this is just homotopy and translation, so it's invertible. And the inverse is also a combination of translations and homotopy, so it has a similar form. So both t and t minus 1 are continuous in the weak topology. And now it's easy to check that t takes this ball into this ball. Okay? Just check. So if x is here, so the norm of x minus a is less than r, you just evaluate tx minus b in norm. Tx minus b is less than the norm of this, which is less than s. So tx is here. Right? So t takes this ball into this balls. And t minus 1 does the same thing. Okay? And it also takes the closed ball b prime r into the closed ball b prime bs, and the sphere into the sphere. Okay? So therefore, all this, so we proved it. yeah, that's it. So this concludes the proof and concludes the video and section 4.2. So thank you for your attention and see you next time.